Hello everybody and welcome to class today. Hope you're all doing good today. We got 6 beers, so we got pretty, I think it says 6 beers, a low amount of beership, so we'll see what happens. But let's go ahead and do this then. So today we are going to finish talking about virtuals, and then we're going to talk about exception handling, and then templates if we have time. So for virtuals, we are going to be talking about 2 special scenarios. One of them we actually have talked about before you even learn about virtuals, which was the issue with the diamond problem. And we're just going to revisit that kind of quickly to understand as to the why virtual fixed that. And then Virtualdestructors we will also be discussing rather briefly as well. But I will be providing you with additional follow-ups that you can read along if you want to know more details about it. So yeah. So what is a diamond problem? I guess let's make sure we remember that, since it's been a while. So I have a little reminder that, or just so because I'm not gonna remember it, upcasting is changing a child pointer to a parent, and downcasting is changing a parent pointer to a child pointer. It's not related to the diamond problem. I just put that to remember. But anyways, the diamond problem. So the diamond problem is basically when we do inheritance, and when we specifically do multiple inheritance. It can't happen unless we do multiple inheritance, and that is why some languages like Java do not allow multiple inheritance. The only way that they allow sort of a pseudo multiple inheritance in those languages is they have what are known as actually proper interfaces, and those are kind of like abstract classes in a way. In fact, they are abstract classes. They're actually kind of like the interfaces that we think of in C++, where it's just like pure virtuals per se. But in their interfaces, I do believe that they can. I think they can have variables in Java. It's been a long time since I did Java, but basically, they allow you to have multiple inheritance of interfaces, but not of actual classes. And the reason why is because they don't want to have to deal with this problem in the first place. So yeah, that's how you do that kind of thing in Java. So anyways, the diamond problem, which occurs in C++ because of multiple inheritance, is when you have a class A and then you have class B and C that are inheriting from A. And now I put the arrow this way because I want you to be aware that sometimes people do it that way, as a way of representing that B is inheriting from A like that. And actually, if you're thinking about a UML diagram, you typically see the arrow in that direction. So anyways, from there, this is perfectly fine, no problem whatsoever. The problem comes in here, and this is where you do the multiple inheritance. So this would be where you would do something like class D inherits from B comma C. That's going to be your multiple inheritance right here. Now you do want to put it here, put in a different color. The word public or private or protected. Well, by default it's private, but if you want to make it public, you put it there. But then also you put it there as well for the C. You don't put one for both. It doesn't like extend that way. So yeah, just reminding you about that. But anyways, that's basically going to be your issue, and the issue is going to arise if these guys have variables. Or even potentially functions too. So if they have like a foo. Because let's say that A had this. So let's say that this has that, and then maybe this is a Y, this is a Z, and this has a J. Okay? So well, let's start with A. A only has an X in the foo, right? But B has access to all two variables here, so it has these three, right? C has access to these guys. D has access to basically everything. The problem is that it has duplicates of the X value. That's the one that you have problems with, and potentially duplicates of the foo function as well. And so, as we saw before, if you're trying to refer to the variable X, you know, if you're doing an object called D, whether it's dynamic or not, doesn't matter, then you can't just do this, dx gets 5, because that is going to say that it's ambiguous. So the pseudo solution is to use the scope resolution operator. So you end up having to say the dot bx like that, okay, and or d dot cx, and then these can have actually different values in them, which probably is not what you want. You don't want to have duplicates of the same variable. It's a bad thing. You want to just be able to do something like that. And so the solution to this is to add the word virtual in front of your inheritance at this level. So when you're doing this inheritance, say class B inherits from A, again, public par whatever, but also you're going to put in there the word virtual. And similarly here. I do think you need to put it in both. And so why does that work? So remember that virtuals are not kept. So remember that compile time binding is basically where you're associating your class members with your class at compile time, not at runtime. And so if you wait until runtime and you figure out that you got two of these, by doing the binding at runtime, it's going to be like, oh, you already have one of them, so you don't really need the other one. And that's kind of like the oversimplification. The more specific thing is that you end up basically keeping a pointer to the object in a v table, in the virtual function table, and basically that virtual pointer is gonna be used. Well, it's kind of like the this pointer. And it is used to calculate the offset of the variables and so on. And so when you're trying to access the objects of that class, you're basically, it's tricky to describe this. You basically how to say this, because the pointer is in the v table and the functions themselves are in the v table, you can kind of say that the variables themselves are also stored, you could say, in the v table, and there's only one instance of them that is created, and both of the members point to that one. That's kind of going to be the best way to really explain that. They will talk more about this in 326, so you can get far more details about this. But for now, I'm going to go ahead and link you to a rather long article that you can read about this if you're curious to know more. What you really should know for this class is that you can use virtual inheritance, which is what this is, to solve the diamond problem. That's kind of the limitations of the class. And then in 326, when they actually analyze programming languages in detail, they will actually tell you more about multiple inheritance and the risks associated with that and why this is really happening. So yeah, that'll be kind of what I want to say about that. And I do have an example of that in Canvas as well. I'll go ahead and put you a link to Canvas right there. And that one is basically what I said. And I show you the two versions of the code, one without the virtual keyword and one with the virtual keyword, and they're controlled with the define at the top, which you can just go ahead and use. In fact, here I can probably pull up the code here so you can just make sure you guys know about that. Here. There we go. So right there. So this is the canvas link. Virtual inheritance is called, and as you can see, I have it defined here. If you turn this defined off as it is now with the commented out defined, then it'll have the diamond problem, and you'll have problems doing this. If you turn it on by uncommenting it, then it'll run the virtual version of that. As you can see, I have the word virtual in front. And by the way, these two order rings don't matter. You can do virtual public or public virtual. It's just the modifiers. They don't matter which order they go in. But yeah, that will basically show you that. So, and here I have like the typical example of the inbreeding, you know, the ghetto solution. And by the way, you can still refer to the variables like this when you do virtual inheritance, but they're just going to be referring to the one only X that exists. Whereas here there would be different X's, which makes things even more confusing actually, if you think about that. And then yeah, that's all I want to say about that. Okay, the next thing is going to also be available, I think, on Canvas, or but that was a link, I think, and that's Virtualdestructors. So there, let me introduce the problem that happens with that requires Virtualdestructors. Okay, so if you have class A and class B, so you know the typical classes that I make. So you have a class A. I'm in pain sitting here because my dog's behind me. And then let's say that let's go ahead and put some constructors and destructors to this. And we can just have them see out A constructor and then B constructor. I'm just going to do it like that because it's a lot of space here. Well, I will space this, tap this though, because that does bother me. I just gotta fix the names. So this is actually A Destructor, and then this is B Constructor and B Destructor. Yeah, there we go. Okay, so I got myself here a Constructor and a Destructor for each of the classes. All right, and let's go ahead and make sure that they're public by putting the modifier inside called public. So for all intents and purposes, like little structs. Now let's go ahead and make a dynamically allocated object of each one, just so so that you can see that this is working okay. Okay. So we're gonna say A and B, and well here. If we just make a pointer, there is no allocation going on, so neither of these classes are being called. Okay, so nothing happens, we get no output, as expected. If we go ahead and dynamically allocate them now, so let's allocate an A and we allocated B, now we should see the constructors being called, but not the destructors, because turns out that we have a memory leak because we've allocated memory and dynamically that we never deallocate, right? So you can even show that with val grind. So we can see here that we have very small memory leak because these objects don't really have like variables inside of them. You know, the classes don't have really anything. In fact, I'm quite curious as to how they can be 1 byte. Like, I guess that's just a disk pointer, but a disk pointer would be 4 bytes. So it's quite an interesting thing to see. I'm not sure, but we do have the memory leak of some sort. Okay, so you know, we want to avoid memory leaks. So what do? We call delete on A and then delete on B. And so now when we call delete, we will see that the destructor gets called for each of those. A constructor be constructor, a destructor be destructor. And if we were to run val grind, we would see that we have no memory leaks, okay? So let's go ahead and expand this a little bit and add in one variable here and one variable there, just because I want to make sure that I don't think the error will happen if I don't have variables in there. We can at the end test it without the variable, but for now let's do it like that. Okay, so yeah, this is great. However, let's just say that in the process of polymorphism, you know, we are going to actually create a pointer of the base class that is pointing to a pointer of the derived class. Okay, so we're gonna do the upcasting. So let's go ahead and just do it here since we don't really need the this one, the A. So we can replace this. And so instead of making this a dynamically allocated object, we are going to make it point to B. Okay, so this is your upcasting. Now because of this, you're like, oh, okay, well, I called delete A, which is going to delete actually B, so I don't really need to call this guy, so we're good to go. I mean, if you call them both, then you are deleting things twice, and that is bad because that will, for all intents and purposes, when you try to delete something twice, you could get away with it. In some operating systems, it'll just be like you can delete as long as you want. But in a lot of them, you are going to get a big, bad, and scary error. Okay, so it's like don't try this at home kind of thing. Right now, we're getting our lovely error that you cannot convert initialization. Okay. Interesting. I had not seen that before. In assignment. Okay. I think we just need to do our dynamic casting for this. A is the parent class. We are putting a child in it. Why is it really complaining to us now? Oh, you're right. My bad. I never did that. Thank you. Good call. Good catch. Good catch. Okay. There we go. So, you know, if we do it like this, then it's 50-50 chance if we're going to crash or not. And as you can see, we did crash because we're deleting twice, right? So in this scenario, because I got a pointer of both types, you know, I can go ahead and call the delete on the class that it belongs to. And then, you know, I don't have a problem with the deleting because I'm deleting once. And B, if I go ahead and check with val grind, I don't have any memory leaks. Now, the problem is going to arise if I go ahead and delete on A but not on B. And so you might, you know, why would this be an issue? Well, first of all, it's perfectly valid that you might actually be deleting on A and only B, because imagine the example that we did last time. The example that we did last time, we had an array of the parent class, like animals, animal pointers, and then in there we were storing a lot of objects of different derived classes, right? We weren't ever storing really a pointer of the animal class because it was an abstract class. But here's the thing about that. When we never actually, I don't even think we even got to deleting the objects. Did we ever even delete the objects? Let's see. Yep. Oh wait, no, that's not the right one. Maybe this one has it. Yeah, we never got around to deleting the objects, okay? And so we will come back to that in a second and finish deleting it. But first we're going to do it with the tiny example here. So here's the issue. In this case, it's very nice because we have a pointer of B type that we can just call delete on B and call it a day. It does work. Everything is fine, as we saw. However, there are scenarios where it will be much more convenient to just call delete on A, even though it's holding an object of B. And the problem is, if you do it just like this without any sort of additional keyword or virtual, you see that only the destructor of A gets called and never the destructor of B. As a quick comparison, let me put this one here. When you say delete B, you get 2 destructors being called. Now let's analyze as to how these destructors are being called and why. This is the correct thing. There should be 2 destructor calls, because what's going to happen is this. B inherited from A. And so first, well, here, constructor-wise, when you're constructing an object of B, it calls it basically, here, actually, I don't need to be explaining this to you. We can just run it with GDB and check it out ourselves, actually. Yeah, that might be a nice thing to do. So let's go ahead and do that. GDB a.out. And then let's set up a breakpoint at the first line of main, which is 17. And then let's run it. Okay, so let's see the order of how things happen here. Okay, so we are starting by seeing the call to new, and the first thing that happens is it goes into B here, into class B, and it is calling the constructor of that. But before it actually really does execute that constructor, it's actually going to go and call the constructor to A, and then it's going to actually execute this constructor. Then it's going to come back and finish executing the constructor of B. The part of the constructor of B that is initialized first is the parameters here. It takes these parameters, and then remember, if we were to call a different constructor other than the default constructor, that would be done right here with colons. And then if it sees no call to any constructor, then it goes ahead and calls the default constructor here. After that, we go ahead and we see that the constructors have been built because it finishes running the B constructor. Okay, so because of that, we see that the A constructor gets printed out before the B. This might be a little misleading because you see the line B constructor entirely, but not the entire line is being run. Only this part of the line is being run. In fact, I think it might be easier for you to see that if I space it out. The one time I didn't space things out, it actually might have helped. Okay, so breakpoint at line 25, run. Okay, so this looks much better now. So when a new call happens, we can see that the top of the constructor of V is being called, but just that piece. And then as we step through, then it jumps immediately, before running the code of B constructor, it jumps immediately to the body of the A constructor. And as you can see, that says A constructor here. It finishes running that, and you can see here the curly bracket of the A constructor, so it finishes that part. Then it goes back and runs the body of the B constructor. It finishes running that there, and then it goes back to main, and in this case, oh, here we go. Here's the printing of the B constructor. Here's the printing of the A constructor. That's the printing going on that we saw. And then now it's going to do the upcasting. There is just one line of code. Okay, now comes time to delete. In this case, when we are deleting of the A, it's going to call the constructor, the destructor of the A. And that is going to be pretty much it. And the program ends. It never calls the destructor of B. Why? Because compile time binding is telling it that this must be an object of A. So call the destructor of A. And that's it, right? Okay, now that is a problem because essentially you never deallocate the variable of the destructors, and you never deallocate anything inside of the B class. Now, right now, actually, the way that I have it set up, if I run Valgrind, I don't think I will see a memory leak. And I don't. So you might be thinking that this code is perfectly fine, when it's not. But the reason I don't see memory leak is because the only time that you have these that you really want to use a destructor in B is when you have dynamically allocated stuff. So let's say that this int y is dynamically allocated. So in my constructor, I would say something like y new int, and then my destructor, I would say delete y, right? And I could do the same thing up here for this one, although I don't quite really need to, so I'm not going to. Okay, so now if I g++ this and then I valgrind it, I'm going to see a memory leak with the same code. And if I switch this over, well, here, let's just run it one more time with GDB so you can see it. Set the breakpoint at line 27, run it. So as we can see, the first thing we see, this is a new call. And then from there, we get the top of the constructor of B, but the body is not run because then first it runs the A constructor. So there's the A constructor running. There's the printing in the screen of the A constructor, and then the A constructor's curly bracket because that function ended. Then now we're running the B constructor, so we're doing the dynamic allocation. Then we are running the printing, so we will see the printing in just a second. Here it is, and then we end that function, and then basically that finishes that. Then we're doing the upcasting. Now comes time to delete, but because we're deleting it on the parent pointer, even though it's holding a child object, it's done compile time binding of calling the function. So it's the same issue we had before where with compile time binding calling the wrong function, except in this case it's the destructor, the function that is calling wrong. And so it only calls the destructor of the child, which does not have the deletion of y. So we never see the delete y being called, you know, and that's it. That's pretty much the end of it. And that's why we have the memory leak. Okay. If we were calling delete with the pointer of the child object, then we would not have this problem. We would be okay. Let me compile it again. Okay, so before I run Valgrind on that version, I'm going to show you how it's running. So set up the breakpoint at line 27, then go ahead and run it. So here we got the new call being run. That calls B as we saw. That calls the A constructor, and then we can see the A constructor being printed. Now it calls the B constructor's new int for the y, and it's running B constructor, and everything is the same so far. The difference is going to come here, right here, when we're calling delete on B. Delete on B, because this time it did compile time binding on an object of B, it is going to first call the destructor of B. It's going to run the body of the destructor of B, and then after that, it's actually going to run the destructor of A, as you can see here, A destructor. See that? So it actually runs the body of the B destructor, and then it runs the body of the A destructor. I know it looks kind of weird in the way that this code looks, because you can see it first did this line, and now it's doing this line, and you're like, huh? This line is above these lines. Yeah. It's just running the in between here, where there would be a call to a custom destructor if you had one. which we don't really talk about doing, but you could have that, I suppose, with parameters and whatnot. And so, yeah, you basically call the destructor of A. You can see here that this pointer is being used because it actually is deleting the actual memory, and that's it. And so that's good because now we actually call the destructor. So as we will see with Valgrind, there is no longer a memory leak. However, we may not always have the luxury of knowing which object it is. We want to be able to just call delete. You know, we want polymorphism. We want to be able to just call delete on this object, and it can figure out on its own which destructor to call based on what it really is. And so for that, we need to make the destructor virtual so that it's put on the V table, and it only decides at runtime with runtime binding which destructor it actually needs to call based on what the real object is. And it's as easy as just putting the word virtual in front of it. I think you can put it on, which one can you put it on? I mean, I think you actually want to put it on the base class, probably. Although, I think you might, yeah. Because the problem arises when you do this, which means you want this one to be the dynamic one. So, yeah. Otherwise, if you do it here, it's not going to help because this is still going to be done at compile time. So yeah, you want it to be done in that one. So if you go ahead and do that, then we go ahead and run it again. Even though we're doing, I mean, if you left it on the B, then yeah, it'll still work the same, and you will still won't have problems. Again, that was never a problem in the first place. The problem was calling it on the base class like that. But by putting virtual in front of it, if we run it, you're going to see that we no longer have a memory leak, as we have fixed our problem. And if we want to see that in GDB, you know, I'll step through this stuff quickly because you've seen this a lot of times. Okay, so here comes the time to delete. So it is going to go ahead and run into not A, but B first, and go ahead and deallocate that. So see, it's deleting B, and now it's going to go ahead and run the A delete. Virtual A. And there you go. So virtual destructors, you know, are used to solve problems when you're not calling it that right destructor because you're calling it on a pointer after you did some sort of upcasting. Essentially, if we now switch over to the longer example that we did last time and we were to run this, I'm pretty sure that we would find that we would run into this issue. We never actually go in and delete things here. So, well, did we ever have a dynamic well, we didn't have any dynamic objects here inside of the derived classes. So that is the issue is there that we're not calling the right destructor, but we kind of, it slips away unnoticed because there's no dynamic allocation, so there's no memory leaks. However, if we had a dynamic allocation in either of these classes, then that error would become noticeable. So you only really need to worry about virtual destructors when you have dynamically allocated variables and you're doing the up and down casting polymorphism stuff. So yes, that's the way the cookie crumbles with destructors. Any questions on that? All right, I will take that as a no. So good. All right, let's go ahead. And by the way, if you want to know more details about virtual destructors, I recommend you check out Geeks for Geeks on virtual destructors, which I did go ahead and post already. So yeah. Okay, so now let's talk about exception handling, and that will kind of go kind of briefly as well. So exception handling is, and you don't have really an assignment on exception handling, but it will definitely be on your exam. What's the sort of easiest way to go over this in a quick manner? Here, let me actually open it up in the book. It's chapter 14, I think. So let's show you how about division by zero. That's a very typical thing. So yeah, let's start with that. So let's go ahead and make a new file first. Okay, so if we have the following code, and then that's I mean I think it might catch us at compile time if we don't do it with cin, but let's just try. So let's say we're doing c out 5 divided by 0. Okay. Yeah. Let's try to see if this compiles. So that's kind of nice. The compiler does give us a warning that we're trying to divide by 0, and it's a good catch. However, if we went ahead and read this at runtime, then the compiler wouldn't even give us that warning. You know, because let's say we're actually dividing at runtime. So let's say this is 50. Now we don't even get that warning because it doesn't know. In fact, we never even divide by 0, right? So if I go ahead and run this, you know, I put in 10 here, I expect to get a 5. If I put in 12, I still expect, well, I expect to get a 4, but, you know, it's not a decimal because it's integer division. So the question is, if I put a 0 here, what happens? And in this case, I get something that says floating point exception, and then I crash, essentially, score dumped. So basically, what is happening is, when you do this division by 0, obviously you can't do that mathematically, so you know it's an error. So the program generates an exception saying like, hey, this is something that I can't compute. Oh, thank you. There we go. So I just went ahead and did 50 divided by x, and x is just a variable that I read in. So if I run it with 10, I get a 5. If I run it with 12, I get a 4. However, if I run it with 0, I'm dividing by 0, so I get this floating point exception core dumped. So again, the reason why this works is because the division is not by 0, which is perfectly fine. The divisor is not 0. When you do make the divisor 0, you know, this is an error. There's no mathematical answer to dividing something by 0. And so at that point, the runtime system is like, what am I supposed to do? The actual CPU, the ALU, the arithmetic logic unit is like, yo, I don't know what the answer to this is. So it generates an error. And that error is essentially what is known as an exception. If you don't handle that exception, the program immediately just stops, and then it basically core dumps or crashes. And so in C++, there is a rather nice way of handling exceptions where instead of just saying, I mean, this one's nice because it actually kind of tells you a little bit, but it's not very clear about, you know, if you had a program with tons of math and somewhere in there was this division by 0, well, then good luck finding it, because all you're going to get is a thing that says floating point exception. You don't get a line number, you don't get anything. That's literally it. That's all you're going to see. And so, you know, you might want more in terms of handling an error. You might want a more elegant way. Exception handling can be very useful when you're debugging. And so while you might not see a lot of usage with exception handling in like production software, or sorry, deployed software, you will typically see it used a lot when they're actually working on coding the software in the first place, so that it makes it easier to debug when you're actually testing it. And so now we're going to talk about how these exceptions are handled and how to take advantage of the exception system. The exception system is sort of a kind of, people came together and said, okay, we're going to sort of work together on create some sort of universal exception handling system for C++ that works the same for all of us, because we could have all our own sort of versions of debugging and generating some sort of error, and here it's more of like a unified thing. And so one of the most basic usages of exception handling is using the assert command, or the assert keyword in C++. The function assert can check whether an expression meets the required conditions. If the conditions are not met, it terminates the program. So yeah, that's the definition of the book. So what I'm going to do is I am going to put the assert in the code before I do the division, just to make sure that it's actually okay to do, to avoid dividing by 0, essentially. Okay, and so it's kind of like an if statement. You say assert x divided by, or x, assert that x is not equal to 0, like that. Okay, and so now if I run the program, I need to include my so assert is in a special library called cassert. Assert, yeah, okay, there we go. And so if I run it, if I put a 5, that's okay. 5 divided by 50 is 10. But if I put a 0, oh, well, I gotta run that again. If I put a 0, I get assertion x divided by x not equal to 0 failed. And I still get a core dump, but check this out. I get a line number, I get a file number, I get a file name and a line number, and not just that, but I get the function name of where that is happening, and I get a printed out version of what I did in the check. And I didn't compile with the -g flag. This is a much, much nicer error. Obviously, this doesn't help anybody who's if I'm, if you're watching, if you're playing a video game and you get on the screen a line of code with an assertion, you're like, what the heck is this? I don't care. My program crashed. So it's useless to a customer. But as a developer, it's very, very useful because you're like, oh, cool. I actually, it tells me that. So why not, the ghetto solution of doing this would have been for you to actually write somewhere here an if statement saying like, if x is not equal to 0, if x is equal to 0, you could write something saying like cout, print statement debugging, which is ghetto, right? So like OFG, I have division by 0 in line 10 of my code of except.tpt, because you might have multiple files, right? So if you're working on a real project. And so, and you probably would want to like return 0 at that point, or call exit or something. By the way, I should put a return 0 here. So that would be the somewhat ghetto equivalent of that. Oh, oops. So the asserts are kind of like a standard that people came up with, which are smarter of doing. I think it's x at 0. Okay, I forgot what the function is to actually exit. So for now, we'll just put a return 0. Which again, might be kind of complicated if you're in a function. That might not even work. Here it works because it's in main. So yes, you could do that, which involves a lot of work, a lot of lines of code, or you can just use your nice and easy assert. Ah, it's a CST live. Okay. Okay, let's just test that part. Exit. Well, maybe we want to do a different status since it's an error. I don't think you need the .h part. I'm thinking of stlib. CSTDLIV. D live, which means the C standard library, by the way. Void value not ignore as it ought to be. Okay, so I guess it is void. Okay, fine. Too few arguments for void function. What? Oh, well, yeah, good point about the semicolon, but I still think, I don't know if that's, oh, okay, weird. All right. So yeah, so now the exit part works. Okay, cool. So we would, you know, we could do the long route like this, put an if statement, put some sort of message that kind of help us out, and then close the program. You know, like this is okay, but then if we do 0, we get that OMG, blah, 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 and so on, which is a lot of coding. You know, it's a lot of coding for that. Or we could use the assert, which is just put whatever you want in the if statement backwards like that, and then let the compiler do the rest of the job for you. Because I mean, yeah, sure, the core dump thing looks very scary, but it's okay because we are getting the error message here with the exact location and the check as to the y. You know, because if you're doing this check and it failed, it means that x must be equal to 0. So assertions are a very, very sort of sleek way of doing some error checking. And again, this is useful in production when you're developing code, because it can make debugging easier. So I mean, hopefully you never have this error where you're divided by 0. But if you are, you know, you might want to see as to how you got there, and this can be very, very useful for that. So that's one usage of exception handling that's pretty neat. Is assertion. Okay. There's also try and catch blocks. So try and catch blocks is, you know, sometimes if you have an error, you kind of want to rescue yourself, right? You want to save yourself from the doom of the error. And for that, you can use try and catch blocks, which kind of, once an exception is generated, like here, you want to try to catch that exception and deal it in a more elegant way. And so for that, you can use try catch. Let me pull up an example actually from Canvas about that. Where is that? Oh, it's right here already. I was like, what? Where is it? But you guys can see it already. Perfect. Great. So let's go ahead and look at this code. Okay? And it's a little faster than actually typing it. So the way that the try catch block works is you write. It looks kind of like a mini scope. You know, you have the word try, and then you got your curly bracket that opens and it closes here, and then you have your catch, which has the word catch. It has these parentheses, which we'll talk about, and it has a curly bracket and another curly bracket that closes. Okay, and so the way it works is when you want to test a code that may generate an exception, you put that code inside of the try part of this. So here, okay? So for example, you might put your division by 0 in here. And if that generates an exception, which you can manually do by writing the word throw, so you could put an if statement saying like, if x is equal to 0, throw d. So you could manually generate an exception for a special scenario which you consider to be an error. But if not, then you can let some classes generate their own exceptions. Like, for example, pretty much most of the standard library of C++, if there's errors, they generate exceptions. And if you go, do I have a link anywhere to that? We'll have this link here. There's a really, really nice link of all the exceptions that things throw. Maybe I can find it. It's, let's see, exceptions, STL. There we go. So these are all the possible exceptions that the standard template library may create. And so you can catch these by using the catch block and catching a specific type of exception. Let's look at Batcast. So a bad cast is when you are casting something that you really shouldn't, and that an error happens. And so when that happens, it generates an exception. It throws an exception, actually. That's the right term to use. And so you can catch those kind of exceptions and then handle them that way. Here's an example of using dynamic cast where the cast is a bad thing because let's see, your cast. Oh yeah, it's actually what we were doing earlier. So we were trying to cast a class that didn't inherit probably to another class. So yeah. Because here they have an object of class bar, and they're trying to cast it into a pointer of an object of the food class. And obviously this is bad. This is insanely bad, right? We were doing it earlier by accident because we forgot to write the inheritance. So this would generate an error, an exception, which then you can catch. And the way you can catch it is that exception that gets generated, you in your catch function, you can use the type of the exception, put a parameter name, and then catch those type of exceptions. So for that, let's go back to my example. It's a little bit simpler. So, this exception that you're throwing here, or an exception that is thrown automatically, like the division or the floating point or whatever, when you want to catch them, you can either catch all of them by using this syntax here, where you say catch, and then you put 3 dots, and then you close the parentheses, which means it's called catch all. It'll catch any exceptions that you get. And when you do catch them, then you can essentially just do whatever you want there. So you can write a cout message, you can close the program, you can even try to fix the error based on what happens, some ghetto solution code and so on, right? Not very useful when you do catch all. That's more of like if you really want to don't avoid crashing a program. Because here's an example where you might not want a program to crash. Let's say, and actually I have used this example in myself. It was in Python, but same thing. I was doing, if you guys know what SQL is, it's databases. And what I was doing with, what is your question? What is the auto within the try? Where is the auto? I don't see the auto in there. Oh, it's just a variable I created. I think I've already talked about it. I was lazy, didn't want to put the word double here. So the auto basically, it's just to hide the fact that I'm actually throwing here is actually a double, So I put the word auto there. But yeah, you can replace this keyword with the word double, and it does the same thing. Auto is the lazy man's way of declaring variables, where you don't put the type, but the type must be defined. So you have to set an initializations of the variable, and then it resolves the type based on what you're initializing with. Because this is a decimal value here, it initializes this to a double, and this initializes to a char, for example. And so you're throwing either a double or a char in this case. In this specific case, you're throwing it a double. But if they say throw C, then we're throwing a char. So that's what that is. So yep, cool. So anyways. In my scenario, I was working with a database that I was generating insert commands for. So like a database in SQL is just imagine the big server with data, and I'm telling it to insert things into the database, okay? And I use that in Python with what's called a MySQL connector, which connects to the database and sends the insert commands with the data that I'm inserting. And I was inserting pretty much the entire contents of Wikipedia. As you can see, that's pretty big, right? Lots of text. It's possible to generate exceptions if I'm trying to insert something that doesn't fit into my database, like for example, just like in C++, I might have an integer that can only fit these amount of numbers, and if I fit a number too big, it might go negative, right? So that might generate an exception. Also, in my database, only was accepting specific set of characters. You can't just put in like some weird accented word in there or a weird symbol. And so if you try to insert that, it generates an exception. And so, I just ran it, and I was like, okay, I ran it, I'm gonna go do something else. And I came back like 5 minutes later, and it had an exception. And the bad thing is, when it generated the exception in Python, the program just terminated. And one of the things that happens in databases is if you don't commit the change at the end, then the changes are temporary. So like in this case, I've only lost like 5 minutes of time. But what happens is, you know, maybe I want to save what I've inserted so far, or I want to continue inserting. So like if one line of code fails, like one line of the database fails to insert, maybe I just want to ignore that and keep inserting the rest, right? That might be a better solution, because while yes, it's an error, like, oh no, I failed to insert this thing, and then this is like mission critical information. Yeah, it's useful to me to know that this failed to insert, but like I was just inserting full Wikipedia. So like if there's a specific line of text that doesn't fit in there because there's some weird symbol, then like screw it. Just ignore that line. I'll deal with it later, you know, make a record of it so I can look at it later and insert the rest. Insert the easy stuff first, per se, right? And so you could use this exception handling to catch an exception and not instantly just terminate the program like, oh my God, exception, panic, just terminate everything. No. Okay, I get it. There's an error. It's not really that bad. Just print out whatever the line of code that failed to enter is and just keep going, you know? Those are the kind of errors where they're not mission critical and you can sort of ignore or just put to the side so you can deal with them later. And that's exactly what I did. I caught an exception. I went ahead and printed out to the terminal what that insertion line, actually I think I wrote it to a file, and then what I did is I just redirected the output of the terminal to the file. Yeah, that's what I did, because otherwise the terminal would just be overcrowded as well. So yeah, I just made it go print the terminal, but really I used lineage redirection to save it to a file. And yeah, I inserted all Wikipedia. It doesn't take that long actually. It took maybe like 6 hours, but still, I don't want like 4 hours into the process to just die and then it doesn't insert anything, right? So that is a good use of exception handling that I can give you from experience. So anyways, while that was in Python, same thing applies in C++. So in C++, when you do generate an exception, you want to look at, if you're using a library, which I was using MySQL insert and connector library, you go look at the library to see what kind of exceptions it generates, or you see the error, because usually when you generate an exception, like it tells you the type. So like here, it actually told us floating point exception at some point, right? Like somewhere there, it said floating point exception. We did division by zero before we used the assert. So you can actually look at that to see the type of exception, and then you can catch that specific exception. Because like you may still want to terminate your program in like a major kind of exception. Like for example, if I lose connection with the database, you know, that's a real problem that there's no point in trying to insert things at that point, you know, just totally give up in that case. So you may still want some exceptions to like terminate the program. And if you don't handle exceptions by the end of a function, for example, it will terminate the program for you. It's not going to be like waiting for you. So you either catch it and terminate it yourself, or you catch them and just not terminate the program, but just kind of deal with them. And so the way you catch an exception is whatever the type is thrown out here, which you can either manually throw an exception, or again, will automatically be thrown by some standard template library as part of the execution, is you use the word catch, and then in here, you put the type of the exception along with a parameter. Actually, you don't even need a parameter. You can just put the type. But you ideally want to have a parameter next to the type so you can read more details about the exception, which typically exceptions will give you. In this specific case, catch X. Int X is not going to give you details because it's just an integer. But in more complicated exceptions or more elaborate exceptions, it will have details, which you can get by calling the what function inside of that exception. You can see that probably in one of these examples. Well, you don't see it there, but you can see it inside of the standard template libraries for the bad cast exception. You can see with what, and it'll actually print to you the type of exception that it is, which is a bad dynamic cast. It doesn't print you the line or anything like that. You may have to call an assert on that, or you can just put a cout that is more detailed. But if this is not a really bad exception, then in the catch, after you catch it, you can say bad dynamic cast, but we're going to keep going. And the program keeps going, basically. When you catch an exception, it's considered by the operating system as dealt with, and it just keeps running the code. You can make your own exception classes, and I think that's what I did in the example beneath here. I go ahead and make a struct called error class, which has a line number and a pointer to the error. And so now, if I have if I have a problem, for example, I go ahead and try to check if a pointer is equal to null, because we know that could be a really bad thing, right? And if it is equal to null, what I do is I just set the pointer to some random stuff. I don't know what. I don't know. Just well, I was going to set it to 7 if it was not null, but if it is null, then I go ahead and generate my exception, which is I have a little class that I created. So I make an object of that class. I fill all the members with what I want. So for example, one nice little trick to know in C++ is that if you ever want to get a specific line of code from C++ from your program, you can just use this command, this variable here, which is, or I think it's macro actually, which is underscore underscore uppercase line underscore underscore. That'll actually return to you the line where the word line is at. And so here I say line -5 because I want to have 1, 2, 3, 4, 5. I want to get this line number up here. And so if I run that, which I can by just click on this ID1 link. This is because, when I was teaching in the spring, I basically did not have a nice little Linux machine running and everything to teach. So I was just teaching on a classroom that had like a Windows machine. So I would basically go online and use an online browser for this. So yeah, so here I can see that I get char exception X and 7. That is coming from well, I gotta edit this. So let's go to fork. Make it private. Let's actually comment out this line so we get that exception. Run the code. Here we go. Error message. Pointer has 0. Line number 13, which is indeed this line number, which is really convenient. Caught at 24, which is where we caught the exception. And then it tells us the value of X, which I don't know what X is. So let's see that in action. So when the exception gets generated, we just make our own object here, and then we throw it. We call the keyword throw, and then we pass the object name. At that point, it exits the block. So if there's, for example, here's a line of code that says throw C. This line of code will never be executed because when the throw happens, it leaves that area of the scope of the try block. So it jumps out of there immediately. Think of it like a break command. And it immediately goes into the catch section of the code. And from the catch section, it's going to go from top to bottom looking for a catch that catches either everything like this, or it catches specifically the type of whatever the catch that was thrown, which in this case is an error class. So because of that, this guy will catch it. So it catches it, and now it runs that code. So error message pointer has, and then I go ahead and print out the parameters of my error message. And then the line number is the line num, which I captured here, which as you can see is correct. And then it also caught it at, and then I call line, where this is the catch. And I don't know, I see -4 because it's 1, 2, 3, 4. So that. Can you throw multiple variables at once with a comma? I don't think you can, because it's kind of like a return statement where you can just return one thing in C++. In other languages like Python, you can, but I don't think you can do it in C++ because it doesn't allow multiple return values. So you can only throw one thing. So if you're trying to throw multiple things, then make a struct to store multiple things in there, and then just throw one struct. So this little struct example that I did is kind of how the standard template library does their own little exception classes. But they use some sort of generic class that is called, in this case, badcast. And badcast contains the throw, the no except, and those things. The constructor, it has a constructor, I guess, and it has a what, and so on. So yeah. What else do I want to say? Well, let's go ahead and switch this code again. So let's edit this. Now let's uncomment that. So this time the exception is not going to be ran because this is not equal to 0. So then we assign send, but then we throw C. C is a char, so it's going to be caught by this exception, which just says char exception 7. If we want to throw something else to see other errors, we could go ahead and throw a not there, but here. Well, if we throw like a 5, that's going to be caught by the integer, which will say integer exception. As you can see there. But if we throw something like a float, I don't think we have a catch for that. And in this case, we're going to get the one that says other errors. Now, you might be asking yourself, or you might be asking me actually, is there, you know, when we talked about like the first day of class about function overloading, and remember we talked about like how to decide which function to get. You know, if you have two functions foo, one of them is an integer and one of them is a double, and you pass in a, well, that's pretty bad. One of them is like an integer and the other one is a string, and you pass in a double. Which one does it go for, the string or the integer? Well, it goes for the integer because it's closer, right? But if you have a situation where you have integer and float and you pass in a double, which one does it go to, right? And I think it should go to the float, but in Java it actually would be like, nope, we are not compiling that code. We're not interpreting that code. Basically, that sort of near distance checking between the parameters does not work with catches. With catches, you either have the exact parameter to catch this with or it doesn't. So like, if in this case where I throw a float, you might be like, well, the integer is kind of close to the float, so it should maybe catch it with that. It will not. It will only catch it with the exact data type being passed as a parameter. So if you don't pass an integer, a char, or a struct of error class type, then it will not catch those. And well, in this case, we have a catch-all that will catch everything else. But if we don't have it, which we don't have to, then in that case, the exception will be generated and the program will terminate in a non-elegant way, which is this runtime error. Okay? So that means an exception was generated at runtime and it wasn't caught. As you can see, if we have the catch-all, then we're good. Okay? So that is the example of exception handling where you're generating your own error. Again, it's important to remember that in your try block, the moment that an exception is thrown, it will stop running code there and immediately go to the catch section. And you do need to have the try and catch next to each other. You can't have code in between them. Like you can't have a random int x gets 5 in between. They have to be literally next to each other to the point where the curly bracket of the try ends and the next character it expects is going to be, after white space if necessary, is going to be a C for the catch. Okay, so you got to have them really right there. It's like an if-else statement. You know, you can't just put things in between the if and the else part. They're right next to each other. So you can also have try, catch, and inception. So I know you kind of said like, can you throw multiple variables at once? You cannot, but you can have try, catch, inception in the sense that like, you have a try block, and inside that try block, you have another try block. And that little try block throws a 20. That 20 is going to be caught by the follow-up catch block. And in that catch, you could throw another exception, which can then be caught by the outer catch block from this try. So, yeah, you can do that. I'm not sure why you want to do that, but you can definitely do that. I suppose if you have an exception handling another exception, like, then things are really bad. Yeah, they're structured like an if-else statement essentially, because that's kind of what they are. You know, if error, then go ahead and do this part. You know, sorta, kinda. But yeah. You got it. So yeah, that's pretty much it. That's all there's to it. We can code an example in here if you want of some specific situation. So catch that will catch anything that's thrown in it. That is correct. It will catch anything it receives. But let's put it this way. Again, it only catches one thing. You know, but you can't really throw multiple exceptions at once, as we saw. So it'll catch the last exception that was thrown. So yeah. And you don't need to include anything, by the way, to use try catch. It's part of the built-in stuff. So I could do something like try if x is equal to 0. Okay, let's throw in an assert in here. Yeah. Let's do that with it. Let's just do that with the current code that we have. So let's put the assert inside a try block, and then let's put a catch that catches everything. And we'll say this Avengers level threat. Okay. And so now, want to put that inside of the try block. Otherwise, it was pointless to try to catch that and then not actually do anything with it. So now let's compile and run. Okay, so if we put like a 50, you're gonna get a 1 out of that, no problem whatsoever. Put a 0, then we did. Oh, in this case, the assertion. I guess the assertions don't generate an actual exception. Yeah, I thought they would. It just flat out stops. No stop whatsoever. Okay, that's fine. Let's get rid of the assertion. In fact, let's just get rid of. Here, I don't want to totally get rid of it because I want to leave it in the sample code. But when I send you guys this code, so we'll leave it here like this. But let's just try to do the division by 0 flat out. Okay, so no error, 0, floating point exception, core dumped. So why didn't we catch that? Let me see what the catch for that is. Floating point exception catch. Cannot catch a handle of floating point exceptions. Ah, I see. So that's actually being generated by the operating system, not even by the thing in here. That's a kind of a special scenario. So never mind. That one will not be caught. Oh well. Let's go ahead and do one that will be caught. So what could be something that could be generated? Here, let me look at the standard template library and see which one we could do. Logic error. That sounds interesting. Most of these exceptions should have examples of what of how they can be generated. Invalid argument. Okay, that one doesn't even have an example. Never mind. Let's try range error. Returns the explanatory string. Yeah, bad outlook. Bad outlook we could see. Yeah. That one. This one we'll try. Okay. Oh, I can't copy paste. That's let me just type it. So we're gonna try to just max out the amount of memory that we can allocate by just making really big arrays until we run out of memory. Hopefully that doesn't crash my system here. And then we're just gonna have the catch like that. Okay. And yep. Let's go ahead and try this out. Okay. Let's check my RAM levels and see. Okay, that was scary. It's not really growing. Let's just make a bigger number. Okay, that should be big enough. I have 32 gigs of RAM, so this is complicated. Okay, let's go ahead and make a string. I think that one will definitely complain easier. Oh, you're right. Good catch. Yeah, I forgot I had that. Let's just get rid of that. Yay, generate the exception. Actually faster than I expected, so now we can go back down a little bit. There we go. So that one is slow, but not super slow. So you can saw in fact, how big did we go? Here we can kind of have a little counter. Hey, let's be fancy. I don't think I've ever shown doing this before. I think it should work in C++. Oh, well, hold on. See out. A line feed would have helped. Okay. All right. So I got this big before it crashed. Okay. So it crashed, but not really crashed. You see, it didn't crash this time. It didn't just generate exception. If we remove the catch-all, you know, let's say we're just catching an integer, then we'll just see the exception. Terminated called after throwing an instance of bad alloc. What bad alloc? So now we're gonna catch this the right way. So we're gonna go ahead and catch it, and I'm looking at the documentation of bad allocs here. By the way, here's that link there. Okay. So from there, it says to do. It's called std bad alloc, and pass by reference to be efficient, and then we can call it whatever we want. The typical name is just call it E, but now that we got our E, we can actually say cout E dot what, so we can see what is in detail. And what else do we get there along with that? What variables do we get? Let's see. Operator equal replaces the bad alloc object. That's pretty much it. That's all there is to this class. So yeah. And this what will basically tell us the same thing here, or it should at least. So there you go, std bad alloc. See, and that is coming from the what function. So at this point, we could more elegantly crash the code, or terminate the program, or we could deal with it by being like, okay, well, I guess let's try it again. You know, let's try to make a smaller array. So this time we're like, okay, well, you know, I guess that, you know, I mean, here, let's say we try to quote unquote make a small array, but really we're just doing the same thing, just to see that, we can try again and then fail again, potentially. So in this case, we're gonna catch all and then say, yikes. Okay. All right. So, okay. Let's make sure we got the right brackets here. So we got this bracket here, this bracket here, this bracket here. No, this should be fine. Expected primary expression. Ah, okay, I see. There's a curly bracket there. There we go. Oh, my curly brackets are kind of messed up. Okay, there we go. Thank you. Cool. All right. So now it's gonna fail, and then it actually fails immediately in this time around. That's interesting. I wonder if that's because we have this massive memory leak. Yeah, that's why. So basically, we have this massive. We're still, you know, we're creating all these memory allocations, and we're not even storing the, you know, because this returns a pointer, right, to the memory. It's just being thrown away. So essentially, we can't even allocate a single one more time. It fails immediately after that. Let's just try to make a really tiny variable now and see if we can even get away with that. It would not. It would take a long time to run this. I'm going to show you here. Oh, it actually ran pretty quickly in this case. It actually didn't run that much. When it got to like 170 in the count, it says new failed and should throw an exception, but Valgrind cannot throw exceptions, and so it's aborting instead. Sorry. So yeah, it actually this gives up around 170. It's like that's already too big. This is indeed at the level of gigabytes. So interesting. So actually, Valgrind is telling me that this thing should have failed around 170, even though it didn't. That does make me curious as to whether that's true or not. Oh, hey, it just finished running finally. Now there we go. We got our little memory leak of 59 gigabytes. So that does make me wonder if here, we can actually do that. We can switch this to a for loop and check that actually. So for int I is equal to 0, I is less than 200, I plus plus, and then get rid of the static and get rid of the plus plus. And so now, let's just make one variable here of that type. Well, actually, in theory, we shouldn't see the exception. But the question is, does this variable actually work? So we'll say int ptr gets new. And then can we actually store things into this? Okay. Oh, 600. So let's see if Valgrind is right about the fact that it's. I think it's probably just Valgrind itself. Okay, we got to get rid of a bunch of. Here, this one. Nope. So I think that's just Valgrind itself is running out of memory, but the system is okay with it because I am able to access that 40 that I stored in there. So interesting that Valgrind said that. But anyways, going back to how we had this. We should generate the exception again like this. So here we go. Come on. There we go. And then failed again. So cool. Because we do have this pointer here, we could totally try and delete one of them just to allocate one more time. Maybe we can get away with that, I wonder. So if we do nptr out there, and then we have it like that, then here, let's actually delete ptr. So we're just deleting one array. But the question is, if I make one more, if it'll crash again. I think it will, but we will see. I might be able to make two instead of one. So yeah, so this time it didn't crash. So I have to make two of them to make it crash. So hey, I kind of rescued part of the program. At least I had a little bit of memory left so I could finish the program. Now with 2, I think it should crash. Yeah, with 2 it crashes. So this is basically the last one that it can fit. And then one after that, it's like, nope, that's already too much. So just an interesting thing. So yeah, that's exception handling. Again, it's kind of a finicky special thing, but there are sometimes good usages of it. Like I said, that my personal experience with that was in Python. So yeah, does anybody have any questions on this? Again, you're not doing an assignment on it, but I will probably ask you one question on the test about it, like maybe to show an example of it or to discuss it. Yeah, we'll see. Again, those examples that I showed are on Canvas, so you can play with them. What does try do again? Try is going to be the part that checks if there's an exception. And if there is, then the following catch catches that exception. All right, while I wait for questions, I'm going to set up the next file, which is going to be on templates. Try and catch have to be used together. They can't be used separately. They have to be together. It's like an if-else that requires if and else. You can't just have the if part. Like, you would ask us to show an example of how to use try and catch in the exam. Yeah. Or I might give you an example and ask you, like, which exception is generated and is it cut or is it not cut? Either or. I hope this is all slowing down. The OS should delete all the memory after I quit the program, but I might have to restart my VM. My fan is like working nonstop. So when we're using try catch, are we checking for exceptions or are we forcing them? Either or. You can be checking for exceptions from something like the standard template library, like I was doing there with the new and delete. Or you could build your own exception handling for basic error checking that you might have, like dealing with pointers or dealing with like something as trivial as division by 0. So you can throw your own exceptions by throwing them with the throw keyword. But I'd say that you could use assert for some stuff, but like 99% of the time when you're using the exception handling in C++ is because you're dealing with other people's code. So when you're using the standard template library, that's when you want to catch codes. When you want to catch exceptions, sorry. That's when they're going to be very useful to check because you have no control over that error checking code. So basically, again, the reason the try catch block became a thing and exception handling is because there's tons of libraries out there. And we had to come up with an agreement and say, like, okay, how do we error handle between all these different libraries? Some people might do one type of error checking, like their function returns a 5 when there's an error, and that's just a thing that, like, let's say the people that did vectors do, and then the people that did a sorting function, they just decided that their errors are going to come in the form of the first number in the array of things sorted will have the error code or something. Like, it's a mess. So instead, everybody came to the agreement and said, we're using exception handling, and we're going to throw an exception of a specific class type, which you can then catch and then handle. And it just makes life easier when dealing with errors that can be generated by other people's code, because now you can process those, you can catch those exceptions and process them, and you could read the documentation to see what kind of exceptions they throw, so that then you can work with them and then you can associate it. Because I mean, yes, other people's code should be perfect, quote unquote, as in like if there's an exception thrown by other people's code, it's not probably because their code is wrong. It's probably because your code is wrong and you're feeding in bad code to that library. You know, like you're trying to sort something on an array that's empty, you know, or like a non-existent array. Or you're trying to use a vector, but you don't have enough memory. So when you allocate some, you know, when your vector gets really, really full, like bigger than what you can fit in main memory, that's going to throw an exception. And so the vector class will throw the exception. And then you want to catch that and basically deal with it by at least knowing that you run out of memory, you know, that kind of thing. My puppy's sleeping. Puppy. So, yep. Okay. So now we will be talking about templates. And templates is a way that we can achieve compile time polymorphism. And it's the second part of chapter 13 after they talk about functions overloading and operator overloading. So templates, you know, so far, when you have to write a function that adds two things together, you know, you basically are forced to do something like this. So int add, int A, int B, pass by reference or value, whatever. But the point is that you do something like A plus B, and then you return the result. So return A plus B, right? Or you could also do something like int answer, and then if you really want to make this like overly elongated unnecessarily, you could do this. I mean, I don't even think you can make it even longer than this, but yeah, this could all be written in one line of code that says return A plus B, but you could do this, whatever, free country. The thing is, if you want to create a function that adds two doubles, for example, then you need to go back. And even if you're just returning integers every single time, even if you're just returning integers, if you want to just make this work with doubles, you got to copy paste and then change these guys to doubles. And you're doing function overloading, which is okay, but it's a pain to be doing this. You know, if I want to do a floats. Now, you can take advantage of the fact that there is that thing I was just talking about earlier with the exception handling, where it's like, you know, if you call this on an integer and a double, well, that one's going to be problematic because it's not going to know which one to resolve to. But probably you don't need to write this float one because you could use the existing ones to do that and you would be okay, right? However, if you're trying to do it on strings, then you got to write it because it's not going to resolve to any of them. However, in the case of strings, A plus B is actually a concatenation, right? So probably here, you actually want to return a string. Right? So now in main, I have achieved polymorphism, compile time polymorphism, because I could pass into these functions something like A plus B, which is going to be just integer addition in that case. Well, the cars become integers. I can also do, oh, I forgot about, actually, what I wanted to do was this. I can also do A plus B, which are strings that are going to be concatenated together. And I can also do 5 plus 4. Why did I put the plus? My apologies. It's a comma because it's parameters. 5, 4. And I can also do, you know, 10.5 F. I think we'll see if this one causes issues. Okay, we'll see which one of these doesn't resolve, if any. Yay, but they all worked out. I just need to add end lines so you can see that better. So, Huh, that's interesting that that gave us actually the B. That's weird. So I expected to get not B on either of the first ones. The oh guys, none of these are looking okay. What is wrong with them? Oh, that's what it is. Yeah, I'm tired. Thank you for catching that, guys. All right, so there we go. Good catch, good catch. Okay, so there we go. This looks more legitimate now. So, okay, this worked by doing concatenation as it should. Yay. This worked by doing addition of 5 plus 4, which is using this one down here. And then this one worked by using actually the integer one still, it seems like. Interesting. So the floats resolve to an integer. If we wanted them to resolve to a double, then we could remove the f's. And then that should resolve to the double. Well, I lost my parentheses, but... yeah, you're right. So it is doing the, it's rounding down at the end. So that is what's happening there. So it's here. Yeah, so I guess let's make this a double so that we can see that it's actually calling the double one. It's not actually, it's not, oh, the answer here still. There we go. There we go, 11.6. So, yep, we got it. So, excellent. The 131 is coming from adding the ASCII equivalent of A and B, which in ASCII are going to be probably whatever that is divided by half. So something around 60 plus 61, I'm guessing. No, 65 plus 66 probably, because that would be 131. We can confirm that with the ASCII table. So, by the way, check out that's cool shirt. Yeah. Okay, go on. Let me double check with the ASCII table. So she just got showered today, so I guess wanted to kind of wear a shirt. A is indeed 65 and B is indeed 66. So yeah, I was right about that. Okay, cool. So this is great. You know, we got this polymorphism using function overloading where we just call add on two things and it adds no matter what. However, it's a lot of typing. You know, we got a lot of repetitive code. And if we want to do this abstraction equivalent of this, we're going to have to write 3 more functions. And if we're doing this with objects, you know, we have an object called A and B, which are like special type of object. Like think of the midterm where you have to do dollar signs. So you're trying to add money together. So you make an object called dollars and you're adding them. It's painful. So templates allow you to basically have to write only a single code segment for all of this. So we're going to convert this all into one function that is sort of a template, as the name implies, to basically other functions that kind of are born out of that. Okay. So the syntax for templates is I'll go ahead and write it. How about I write it on the iPad? It's quite simple, but at the same time can get kind of tricky once you're dealing with class templates. So we'll start out with the basic ones. There's going to be 2 main templates we're going to be talking about: function templates and class templates. Today we're going to do function templates. Next time we'll do class templates probably because we won't have time. So templates are meant to make your life easier, not harder. So please don't make your life harder with them. Okay? So templates, if you want to create a function template, you will do something like template the keyword template. Then you put in a class type. Actually, no, you don't need the curly bracket there. I'm thinking of something else. And then you go ahead and give your function definition. And I do have code on Canvas, I do believe, for templates. It's called template sample code. You gotta actually click on the thing that says IDE1 to see it. I guess I never copied the code from the IDE1 to the template thing. Yeah. So if you look at the first link, FOHX, this link here, you can see an example of a function template. And we'll do one here in a second, but yeah. So essentially, this looks all scary, but finally we are going to learn about using these things. Because when we use vectors, we were using templates. If you remember when we're creating a vector, you know, we basically said vector int a, you know, something like that, you know. And so this told us that we're making a quote unquote a vector of array of, but it's a vector of integers, right? So, you know, it's a lot. Back then, I basically hand waved and said, yeah, these things are. We'll come back and talk as to why the syntax of this is like this. But now that time has finally arrived. That's because it's using templates. And so when you're making a function template, what you do is if you're actually doing an actual example, not just a sort of a syntax thing as it is here, you do write the word template. And then you say class, and then you get a variable name. So we'll say class A. And then you can use that A to substitute the type of whatever you're templating per se. So if we're doing the addition, what we would end up doing is, if we want to return always an integer, we can, but in this case, we're going to return the same type. Actually, we'll just do an integer. We'll do the baby example first. So we'll say int, then we'll do the add. And then in here, in the parentheses, you know, these are going to be templated variables. So we're going to say A, you know, we had them called A and B. So I guess to not confuse you, let's just use the word T for that. So otherwise you might get confused between the A and the lowercase a. So we'll use class T, okay? So we can do something like TA, comma, TB, okay? And so now, inside our function, we can go ahead and create variables of this type. So we can say T answer as we had it. We can then do answer equals A plus B as we had it. And finally, we can also do return answer. And there you go. You have now written a templated function. So let's go ahead and plug this in the actual code. So template class T int add TA TB, and then here the answer. And again, this could all be written in one line of code. In fact, I'm going to write that one line of code beneath it. Yeah, return answer. This could all be written in one line that says return A plus B. Just FYI, okay? That's like the shorthand. But yeah, this is good because you can see that you can do declaration of variables as well. And if you do this, right now it's gonna be iffy how it runs because we have the string one. So let's go ahead and comment that one out for now. But for the other ones it's gonna run, it's gonna cast everything to integers at the end. So you can see here that the 9 is okay. And the 11.6 became 11. This became a negative 125. I don't exactly know the reason why, but I'm going to assume that I don't know. It just became 125, which is kind of weird. I wonder why. I'm trying to think as to why it would become a negative number. I'm guessing that the way the car is kept. No, but that I'm not sure actually. That's weird. That's the why it became a negative. I'm just going to ignore that. No, it's just I don't know. I mean, I think there's a function in C++. There's one in Java, or sorry, Java, in Python that gives you the type. Is there one in C++? So we can see the type. C type of variable C++. It's possible to print the variable type of. Okay, so let's go ahead and actually see out here type of A, and then maybe inline, or no, it's just some spaces. Type of B. I want to see what these are being considered as. Okay. So big verb indeed. Expected primary expression before that. Type ID, or actually no. Type ID maybe. I think this one works. I don't know. I've never done this in C++. Must include type. Yeah, it's not gonna work as a template. Okay. Yeah, I do not know. It's a big mystery that we will never know. I think we can try to see out A and B, and as to see as to what they are and why it became a negative. Oh, I forgot these things. I'll try that in a second. So inside the function, they are indeed A and B as characters, but when I add them together, they become a negative number. That is so weird. I don't know. Let's try. Let's try to see if the type thing will work with that. Type ID a dot name. We'll see if that returns something. Must include type info. Oh, it's asking me to include a certain library. It's a car. Okay, so that actually worked. Cool. Let's actually put the second one there. So I guess this is the way that you write type name in C++. Type ID B dot name. So it says they're cars, and then this says they're integers, and then this says they're floats. And I'm assuming that if I try to do the string one, it would complain because it's trying to return a string as an integer, which is a bad thing. So yeah, that one does complain. That's okay that it complains. I do not know. But anyways, let's try to do the thing I was going to do earlier. So let's actually make the return type be of T type. So the template itself. Maybe that'll fix it. I mean, maybe that'll... Now we just get a weird question mark, which is returning a character that's negative. Okay, that makes sense as well. But I don't know. I don't know what to tell you. This is one of those big mysteries. So maybe the type ID answer. Oh, yeah. That could help as well. As to start to find out. Maybe, yeah. So cout type ID I think I know why. I think I know why now. But let me do this first. This should say character. But I think I know the why it's doing this. Yeah. This is like some tricky, nasty stuff. Okay, so this is still a character. So I think I know why. Okay. So I think this is why this is happening. Okay, this would make sense actually. If we look at the ASCII table, let me pull that up. This is actually kind of cool. Interesting error. Like this could be like maybe I'll remember this, and then like in the fall I will ask this as an extra credit question in the final exam. And like if somebody gets it, I'll give them like lots of points. So I guess if you guys don't pass the class and take it again in the fall, then you can take advantage of that. But so here's what's happening, okay? So what is 65 and 66, as we said? That's 131, right? That's what the addition should tell us, right? So what is happening is this. Because it's a car, the biggest car that you can have is 127. And so the count only goes up to that much. If you have 128, it flips back to a negative. So it goes back, it basically overflows. And so because A plus B is equal to 65 plus 66, which we said is 131, it is overflowing by 4. And when it overflows, it starts counting from negative. So it goes from 127, it probably goes to negative 127, negative 126, and then negative 125, which is how we get negative 125. It might go to negative 128 first. And that is why we're getting the negative. So do you guys see that? Like, do you see why that is happening? It is like an overflow that's going on. I think it'll be easier to see if we try to add something that is a little bit smaller than A and B, so that it shows us like right for the last symbol. So like, for example, the smallest thing that we could easily see is 126. So if we want to do 126, we can do, I think, this one, because this is 62. So 62 plus 66 is going to be, my brain tired. Let's see what that is. 62 plus 66 would be 128. So that's a little bit too big still. So if we go to 60, then that is going to give us 126. So yeah, so let's do 60. So 60 is a symbol less than. So the other one, okay? So this one, if we run this like that, then we get back 126, which is a positive number, right? What we expected. And if we switch this to a car, we would see that that would print a tilde right there. See that? Okay, cool. So now, switching this back to an integer so we can see the issue. If we go bigger than this, if we go one character bigger than this, so here we'll do it with the C so we can manipulate it easier. This will become 128, or 127, sorry, from 126 to 127. So from 126 to 127, which is the biggest thing in the ASCII table. See? Right there's my ASCII table. And the 127 is the biggest one. It's the equivalent of the delete. So if we go one character bigger, then that is going to flip and is going to become negative 128. And it did. See that? So yeah, that is exactly what is happening. So ASCII magic indeed. And so that is because it's going to overflow. So it basically, if we think about the way that this is binary representation of this, the biggest ASCII value, I believe 128 is 2 to the like 5 maybe? No, 2 to the 7th. Yeah, 2 to the 7th. So that means that we have 1, 2, 3, 4, 5, 6, 7. We need. I think we. Here, let me double check. Binary to decimal converter. So if we do 1 0 0 0 0 0 convert, that's 32. Another 0, that's 64. So that one. So we have 2, 4, 6, 7 zeros. So okay. So this. So basically, the ASCII equivalent of that, so 2, 4, 6, 7, so 0, 1, 2, 3, 4, 5, 6, 7, is 127. So this is the ASCII equivalent of of 127. When you go +1, the next number is 1000000, which is this one up here, okay? The computer looks at that number, and that's the sign bit. That's used to keep whether this is a positive or negative. So instead of keeping a range of 256 numbers, it keeps the range of basically -128 to 0 to 127. So that's why it flips and overflows, okay? So yeah, so it's using that last digit as a sign bit, which is why we get that. So that's a really interesting error, actually. That's very tricky. Like, you know, you really have to think for a second there to figure out why that was the case. So I'm kind of happy we faced that. That's a cool thing. Like, you know, respect. I'm actually pretty happy that I solved that, because I would have been disturbed by that for a long time. So yay, we got that. So I know that wasn't the focus. The focus was templates. You guys see an example. We will revisit templates tomorrow. We'll spend probably the full day on templates, and then if we have time, we'll talk about recursion. But yeah, that was pretty cool. So, and like I said, now I have a really good idea for the extra credit in the fall for that, because I don't think anybody's gonna get that. But if they do, then hey, respects, you know. So yes, that's pretty much it. That's the class for today. We shall continue talking about templates tomorrow in detail, since we barely just touched it. So tomorrow is Wednesday, so we will do templates tomorrow and then introduce recursion. And then Thursday we will spend the whole day on recursion, and then next week we will maybe finish recursion for Monday, and then do linked lists on Tuesday, Wednesday, and then if we have time we'll do arrays and stacks and queues on Thursday, and that'll pretty much be the end of the semester. Actually, no. Thursday is your exam. So we only have 3 days of next week. So really, in that case, linked list we have to do Monday, Tuesday. And then Wednesday, we will do maybe half the class linked list, half the class in queues. Are you going to increase the extra credit to 100 points instead of a 50? Because I remember you talking about how inflated it is. You mean like the Twitch extra credit? I already have it as 100 points. So if you have been claiming it, I should have given you in increments of 100 points. If you have 50 points, that means I made a typo. So let me know on Discord. By the way, there is one person that claimed the extra credit yesterday that didn't tell me who they are. So it's just kind of floating there because I don't know who to give it to. So person is Adider77. I don't know who you are. So let me know on Discord. Yeah, the class is supposed to be over on the no, because we don't have class on Friday. See, this is a Monday to Thursday class, which means that technically speaking, we should have the final on Thursday. I wish we could have it on Friday, because I have my other class final on Friday, the 219. But technically this class ends on Thursday, so it sucks because we lose a day. So because you have the exam on Thursday, that means that we only have 3 days next week. So what I might have to end up doing is, if there is some kind of review, I will have to do it outside of class time, maybe right after class ends or something on like Tuesday or Wednesday, because I will need the time so that I can finish talking. Because linked list will definitely take us 2 days to do, and recursion should take us 2 days to do. So if we do recursion basically Thursday, and then piece of tomorrow and a piece of Monday, then we can do 1.5 days on linked list, or 2 days, but then have a half of the class left on Wednesday to introduce stack and queues. But they will go over stack and queues in 302, so you'll be fine about that as well. So yes. Oh yes, hello. Yes, please let me know who you are, because again, I don't know who you are. So how much is a note-taking extra credit worth? That is very, very big extra credit. I don't give a specific number because basically, if you have like an 84%, that could bump you up to the like an A-, for example. But like if you have an 85, it could bump you up. But if you have like an 82.5, I want to be able to bump you up. So I don't say a specific number, but basically it'll bump you up a letter grade. However, the extra credit is a 2-part process. You have to do the notes, but also you have to do the timestamps for the videos. So yes, that's why it's a lot of work. So you get points. There's also another extra credit now, which is the debugging of the app that I posted on Discord. So go ahead and check that out. information on that. I have a question for assignment 6. When I try to call the get ID function with debug on, it says that the function does not exist. Is there a specific way to call those functions? Maybe it's because it's private. I'm not sure. I don't remember the get ID function in detail. But the way the debug works is how defines work, which is a define that it's defined, so like it's not commented out. When you say like if defined A and you already defined A, then it runs that piece of code, and it also looks at it when it's compiling. If it's not defined, then it doesn't run that code, but more importantly, it doesn't even look at it when it's being compiled. So it would make sense to say that it doesn't exist if you have the debug off, you know? So maybe you're flipping it around. That's what I could think of. Are we writing code for the extra credit, the report? For the bug report, you're not running code. You're you're basically running the app, and if you find an error in the app, like a bug or an exploit, if you're fancy, you can try to exploit it. But if you don't want to, if you just find some error, like a visual error, for example, let's say that it's asking you to enter your first and last name, and this has happened in the previous app. People were going to enter their name, and the text was invisible, and that's because the text was just the same color as the background. That's a bug, right? It's a thing that people can be like, what the heck? That's the kind of thing you want to report. And then you take a picture of that along with the text, and then you send that in the post, and that's it. So in our code, we can use a define debug to use the functions in debug. Yes, which should help you figure out the solution. And then once you have figured that out, then you turn off debug, and yes, it still work. But it's kind of like to kind of cheat and look at the answer and then work your way without using it. So yeah. And yeah, you can see all the information in that specific text channel that I've created for that extra credit. How do you turn on the debug afterwards? You comment it out. You just comment out the line at the top of the header file that just says that says define debug. Just comment that line out, and then it'll basically. That's probably what's happening. So you're probably not aware about that. So in your header file, I believe it's in the header file, but it might be in the main file. There is a line of code at the top that says define debug mode. If it's commented out, none of the code under the debug flags are going to run. So you need to uncomment that so that it actually runs. So that's the two modes. So just switch back and forth so you can see it. And then write like a cout statement so that you can see when it runs and when it doesn't run. Which I think I do have a cout statement that says like debug mode activated or something. So yeah, you just uncomment it. That's it. Where is this? I can find this. Okay, there we go. So, any other questions? Well, you can't except for that one line of code. That's the one line of code you can't touch. So, yes. I mean, temporarily, but when you do submit your final project, you basically want to leave it off, which is how it currently is. But you can do that in the meantime. I mean, heck, you can do whatever you want in the file while you're processing it. But before you turn it in, it's got to work in my version of the header file, which is that one. So you can have debug mode to explore, but eventually before submitting it, you got to make sure it works without it. But it's useful to see the memory addresses. So you never answered this question. Which question? Now you left me with a cliffhanger. Oh, were we allowed to include vector library for assignment 5? No, I did answer. I said no. Yes. So and then you sent me an email. I said no. So you can't use the iterator stuff. Essentially, you don't need to, because if you're just making dynamic arrays, you can use a regular for loop. So you don't want to do that. If you did, it's okay, but like you're not going to lose points for it. But if you only use it for the iterator part, but you didn't, you shouldn't have needed to use it essentially. If you wanted to stick to the range for loop, then yes, you have to create an iterator, but you shouldn't have been required to use it. So yes, but I did answer it on Discord. So anything else? While you guys think about that, I'm gonna close the VM and restart it, because I think all that memory allocation stuff is kind of killing it slowly. See, I'm even gonna show you. Sorry, the application memcheck AMD64 has stopped unexpectedly. So yeah, we killed it. We killed the VM. It's just slowly dying right now. It's like on its last leg. Valgrind program. So we really hurt Valgrind here. So installed on 2011. Oh my god, this VM is old. Is it really from 2011? It might be, actually. No, that's not true. No, it can't be that old. Oh wait, I'm looking at the 11 here. It's 2016. That is true. That is probably that old. I probably did install this in 2016. So I mean, this had Ubuntu with like 14 in it. So yes, we definitely hurt this VM. I did install a new VM. I just have to actually switch to using it. So okay. Anything else, guys? So yeah, I'm gonna restart that VM, give it new life. Because you know, what's the first thing they tell you in the IT world? How you try restarting it? How you try turning it off and on? That's what they say, right? Yeah. So I think it was 2016. Yep. I mean, frankly, it's the truth. A lot of the problems can be fixed by just restarting a system. It just kind of refreshes things. So it's to be expected. But okay, it's back up and running now. Actually, now that I restarted, I'm going to shut it down as well to make sure that I can restart the VM software itself. So, yep. There we go. I am going to restart it now, because otherwise tomorrow I'm going to start class and I'm going to realize the VM is not running and it's going to be like, oh, you have to wait for it to like fully load. I don't know what you guys are talking about. I'm assuming that they stole that quote from in general and put it in the show now. But oof, I forgot about that. When you restart the VM, it resizes all the windows and gets you some scary errors. Everything is black now. That goes up there. All right, I'm gonna finish messing this up on my own. There we go. Okay, I got it back up and running now. You can even see like the light change because of how orange this is. Cool. All right, thank you all then. I will see you guys tomorrow to finish talking about templates. Have a good night. See you soon.